So Carspec et al. Concluded with, it remains an open question how the AMOC discrepancies between products is impacting progress in decadal climate prediction. It's one of the foremost challenges of our time, is being held back by data assimilation. Hopefully I have your attention now. Okay, so yeah. Coupled data assimilation and being able to use atmospheric measurements in the past, because those are the ones that are most dense and extend over the longest period of time, and perhaps also the paleo proxy observations that I'll talk about may provide a way forward. And there's some interesting ideas about how to do this. Okay, so now you're hopefully sufficiently motivated. Now let's go back and do some of these basics. What is data assimilation? So one of my definitions is that it's a statistical analysis technique that combines measurements and prior information. We often think that this prior information comes from a numerical model, but it need not. It could come from some other source. We often think about it cycling the model in some sequential fashion, but it need not. And like I said in the earlier slides, this provides us with many hooks with other tools and techniques that we can use, like observation impact, optimal sensor placement. Where should we go to place the next sensor? We are resource constrained. We have a limited budget. We like to have the maximum impact in some performance measure. There's a rigorous mathematical foundation for doing that. And model calibration is also a bit of a Wild West problem that I think machine learning may ultimately provide us some big help with. So taking first the Bayesian view of what this problem is, one way we can state it. It's the probability of the current state taking on particular values conditioned upon all current and past observations. And using Bayes' rule, we can say this is proportional to a likelihood function. That is a function of the field on the right, which is the state. So given that the state takes on certain values, we get a certain set of measurements. And this is multiplied with another conditional probability that the current state takes on a certain set of values given the past measurements. So this provides a recursive algorithm. We can use a model to update this. We get these by our measurements, and that allows us to get the thing we want, which is that conditional probability of the current state based upon everything we've measured. Okay, so like Eugenia, I'll do a scalar example right now and visit the same locations she visited with a few extra nuggets. So basically for a scalar, this becomes very straightforward. We have the observations, we have the prior, and this is one nice reason for using the Bayes approach, is that it extracts this notion of a prior from this framework. There's other information that we can bring in. And if we assume, which we pretty much have to do for the high dimensional problems, if we assume these errors are Gaussian distributed, that is, they take on these Gaussian forms for the conditional probability of the prior and the likelihood for the measurements, then this gives us what we want as a product of two probabilities. If we take the log, the negative log of that probability, we get this thing that you talked a lot about yesterday, this J, this cost function. So this is one way to get the J, but it's not the only way. So you can write this down from least squares approaches, but it just falls out naturally from the Bayes approach. And in fact, for those of you that are knowledgeable on information theory, this is pretty closely related to Shannon's information. So Shannon's entropy is P log P, which we can essentially view as proportional to this cost function. Okay, so now this provides us with two ways to solve the problem. We can now start with our J, and we can obtain a direct solution, as we talked about yesterday, by taking the derivative, setting that to 0, and solving for the extreme point, which gives us our analysis. And it's, I think, really elegant. We get this weighted linear combination on the two pieces of information we have. We have the prior and we have the measurement. And if we have no error in the measurement, that is, the error variance in the measurement is 0, we place no weight on the prior. There's no need for the prior if you know you have a perfect measurement. And vice versa. If the background has 0 error, you put no weight on the measurement. But it's all about the error. From my point of view, that's what the whole exercise is about, is getting the estimates of these two things correct, because that provides the fundamental weighting. And so if we do a little more algebra on this, we can remanipulate it into the form that Eugenia showed yesterday, where we can write it as our background plus some weighted new information. We call that new information the innovation. It's the new thing we've learned that we didn't already know in the prior, right? So we knew something from the prior. If it completely agrees with what our measurement tells us, there's no new information here. This is a 0, and we just stick with what we knew, our prior information. The bigger that difference and the heavier the weight, the more we're going to depart from the background. And so K is the analog of the Kalman gain for a scalar. It's this ratio of the error in the prior to the weighted sum of the variances in the prior and the measurements. And if you plot these things, for this scalar, this is just an example of what these Gaussian distributions look like. I think the visual conveys a lot of the mathematics in one shot. So if we have the Gaussian distribution for the prior given here in the blue line, I have another one here. It's called the proxy because I was pitching this to paleoclimatologists, but it applies generally. The end of that exercise gives us this red distribution. That's the analysis. So it has higher probability density than either of the two things we started with before, which means it has less variance, which means we have a more certain estimate of the state than we did with either of these two things we started with before. So if you're a measurement person, you think you know what's going on. If you're a model person, you think what's going on. The data assimilation person is the one who really knows what's going on because they know how to use both sources of information. This black line shows you the cost function. So we found this curve essentially analytically by taking that derivative and setting it to 0, and we knew exactly how to get to this point. So the variational approaches that you were working on yesterday, 3D var and 4D var, say that, well, we can't really do that in a high-dimensional system. But what we can do is design places that roll the ball downhill. To go down, design a descent algorithm, and look for walk down to the bottom of this valley. And if it's a smooth landscape, and hopefully we haven't stepped in a local hole that's not far removed from the global hole, we'll get to the same spot. Although in high dimension, there's no proof that you'll get there for sure, at least not one that I know about. Okay, so let's extend this one step further. Let's stick with this scalar, but rather than one measurement, let's say we have P of these things, and they're independent and identically distributed, right? So they're all drawn from the same distribution with the same error characteristics. We get, for the analysis variance, the exact same expression, except it goes like 1 on P. That's not a surprise. But even if we have really, really noisy measurements, as long as they're unbiased, we get asymptotically close to the true state. So it's not a problem if you've got super noisy measurements. As long as you can gather a lot of them, you can learn a lot about the system. And I wouldn't say a lot of them characterizes the paleoclimate problem, but we have a fair number. The other thing that I will revisit several times is that this is the same thing as assimilating one observation that has been averaged and has an error variance of 1 on P of the variance of this distribution for the measurements. This is sometimes called a super observation because you're effectively averaging over the observations and using that one. Sometimes we do this in the weather world because we have too many to deal with. They are within one grid cell of the model, so a very effective way of compressing the information. But I'll show you this afternoon, and maybe even a little bit later in this lecture, that there are some nice ways of generalizing this idea of averaging to boost signal-to-noise ratio in data assimilation. But that's the first taste of it. What time do I go till on this first lecture? Is it 50 minutes or 45 minutes?
1 hour.
It's full 1 hour, so it's at 10:30. Okay. Okay, so then if we go and extend this to arbitrarily high dimensions, you get that expression that Steve showed yesterday in the practical session. Our cost function has, in this formulation, two contributions. One is the departure from the state, and this is weighted by the inverse of the error covariance matrix for the prior. Another contribution from the measurements and how they depart from the prior estimate, weighted by the inverse of the error covariance matrix for the measurements. In practice, this is often augmented with lots of other terms. We can add other things onto this cost function to penalize certain properties in the solution. But from these two contributions, that's what you get. And you go through the same exercise, and you get the same expression we saw for the scalar. There are some key additions to that story. This K now becomes a matrix, and so we have the variances of the state variables along the diagonal of B, and we have off-diagonal elements which involve covariances, that is, relationships between locations and different state variables. In principle, we have the same thing for the observation covariance matrix. The diagonal elements are variances, off-diagonal elements are error covariances. And now this thing right here is the analog to R. This HBH transpose is the expected error covariance of the measurements estimated from the prior. Okay, and this H is also new. This is the thing that maps from the state space to the measurement space. And in the weather world, we usually know this fairly well. Sometimes it's complicated and sometimes it's very sensitive. Things like radar operators can be sensitive to the hydrometeors and radiative transfer models. Other times it's simple interpolation. And blocky H is the...
So transpose is missing on the right-hand side.
BH transpose. Yes, thank you. Sharp eye. Hopefully it'll make a return visit in later slides. Okay, so I'll give you my recommended background reading sources for this material. Of course, Eugenia's book is required reading. Carl Wunsch's book is really, really good for providing a comprehensive treatment of the least squares approach to state estimation. There are a lot of kind of small details in there that you won't find many other places. I really like this one. In Physica D, it's a paper that's a Bayesian tutorial, and it's got everything in there in a small space. It's really chock full of information. And I can't resist guiding you toward the last section of my book with Jim Holton, where we have one section on data assimilation, but it's everything I could put in 10 pages of that book. So if you're looking for a really concise primer, that's another decent source. Yeah, so for practical solvers, which is what I'll be talking about, I really can't go through all of this. I think you got a good taste of the variational approaches yesterday. Most of my experience is with the direct solvers with approximations to the Kalman filters and square root ensemble filters at that. So that's the last thing I'm going to talk about here. And basically what's going on here, and I think you'll work on this in the practical session this afternoon, is that we don't resolve the error covariance matrix, that B. We use a sample estimate, and we use a shockingly small estimate compared to how big the state is. And we use deterministic observations. That is, we use the measurement values themselves and the error characteristics, the error variance that they're thought to have. And that contrasts with one of the other ways of doing which is to perturb the observations and expose each ensemble member to a different actual value for the measurement, consistent with the error statistics of the measurement. For the square root filters, there are many different approaches. They're all statistically equivalent, but These differences arise because matrix square roots are not unique. You can always have a unitary matrix walking down the middle of that that makes the individual components non-unique.